This is a presentation that was intended for the 2020 APS March meeting on hybrid sensing approaches for quantum spin centers. I'm Michael Flatte, and this is work that I did in collaboration with Joost van Bree and Nick Harmon, and it was supported by AFOSR and the DARPA DETECT program. Some images from my group are shown on this slide, including other topics in quantum information and in spin coherence in solids. So we are interested in systems that have room temperature spin coherence, and one of these examples is the nitrogen vacancy center in diamond. This is a defect which corresponds to a missing carbon atom and then a substitutional nitrogen atom placed next to it, as shown here on the left. And in addition to having a ground state spin 1, when it is negatively charged, this object is optically active, as indicated on the right. It has fluorescence that can be detected, and that fluorescence is an indication of the spin state of that spin 1 object. Now, measurements have been done at room temperature of the spin coherence in these systems, and the spin coherence times are quite long. This is one early example showing a T2 of the order of a millisecond. Longer T2s have been observed at this point. And as a result, there are possible manipulations of the NV that are quite remarkable. Shown here is a sequence of events that one can do in order to initialize and then manipulate and then detect the spin in the NV center. One can initialize with light, which preferentially occupies the spin projection equals 0 state along the NV axis. This is the MS equals 0 state, as indicated in the axes on the right over here. And then that state can be manipulated with microwave fields, as indicated in the sequence over here. And then it can be read out optically. And so the results of that are indicated on the right here with the experimental results, with an analytic model, and with a numerical simulation, all of which are described in this reference here. And there is an effective spin 1 Hamiltonian for this, which is indicated down below. It includes a Zeeman term, it includes a zero field spin splitting term, this middle term here, as well as a term that couples to strain and electric fields. Now, the optical component of this is occurring because of intersystem crossings, where the triplet and singlet manifolds communicate through these intersystem crossings. And that cycling transition allows both initialization and it has an effect on the readout that allows readout for the system. And so that permits single spin measurements even up to room temperature in the system. Now, what's the general aspect of the NV spin that's so attractive for doing coherent manipulations? Well, that's shown a bit here on this plot showing energy scales on a logarithmic scale and indicating that the states that can change, well, the charge channel for this system typically has energy scales of the order of volts, even though the spin can change with perturbations that are only micro EV. And the thermal energy lies in between these two. So as a result, you can't occupy other spin orientations through just charge excitation and other kinds of battering around by the environment. You also don't have access to other orbital states. So all the dynamics that is allowable, even at room temperature, is in this spin channel, where it's only sensitive to things like hyperfine fields, spin orbit fields, or Zeeman or other dipolar fields. And So that remarkable configuration is what gives the NV center its attractive characteristics. Also indicated on the right are some characteristic examples of what's important for the system. So in the red is the aspects I just talked about, the orbital and exchange energies that quench the charge channel, which means that things like spin-orbit interaction is strongly reduced. The other element that's important is that there are very few free spins in the matrix. This reduces magnetic noise that would otherwise decohere the spin. So that's scattering from other excitations or electron-nuclear interactions. All right, so how would you then use this NV sensor to sense magnetic fields? Well, again, in this reference down here, there's a description of how this might work, where the NV is used to detect the field coming from a scanning magnetic tip. The presence of this Zeeman term here is going to produce two different precession frequencies, which can be detected. That's what's plotted out here in this three-dimensional plot. And so by measuring the precession frequencies, it's possible to determine what that magnetic field is going to be locally. And that's going to even be applied to systems that are somewhat surprising. This is sensing magnetic structures in living bacteria. So this is all at room temperature. These bacteria have little magnetic domains in them, and the fringe fields from those can be detected through the setup that's shown in the upper left. Now, there are other types of detection schemes that are possible. One example is detecting the temperature. So the zero field spin splitting, which is this green boxed term up here, is coming from interactions that change energy as the size of the lattice changes. So as you bring spins closer or farther apart, you're going to get a different splitting here. And so a measurement of that zero field spin splitting will tell you what the local temperature might be. Current sensitivity for this is on the order of 100 hertz through echo techniques, and that allows a very sensitive temperature detection. Now, there are other kinds of approaches that one can take to sensing, and here's a new one that we report in this publication down here, and it is very similar in perspective or in terms of the quantity that is detected to the temperature sensing, but instead of sensing temperature, we're sensing the back action of a nearby magnetic material. So when you have a spin center close to the surface, it will produce dipolar fringe fields, which will go out into space and interact with whatever is around. Now, the presence of a paramagnetic material or a diamagnetic material nearby is going to change those flux lines, which can be described as an image spin that will act back on the NV spin. Since the direction of that changes with the direction of the NV spin, the effect of this is identical in symmetry to the zero field spin splitting. And as a result, any measurement approach for measuring zero field spin splitting can also be used to detect this magnetic back action. So let's take a look at what these image currents look like from a spin. Shown over here on the left is our NV center, and then the image spin that's coming from that, which is described as a current density indicated here. And then the size and effect of that depends on what the magnetic permeability in this second region is going to be. If the permeability is 0 in there, then field lines are excluded from the region. If the permeability is 1, then there's no change on those field lines. And if the permeability is much greater than 1, then field lines are sucked into this region and prefer to be in this second region. All of this produces an effective action back on the NV spin. Now, we can look at the size of that effect as a function of NV distance from the sample. That's what's shown here. So The x-axis here is the distance between the NV center and the interface in nanometers. Y-axis is the change in the zero field spin splitting in kilohertz. And as a reminder, in the bulk of material, about 100 hertz is the detection limit. We note that NVs near the surface have a shorter spin coherence time, which is the explanation for this different curve here, because the NV would have to be near the surface of diamond in order to be so close to the sample. But even with the surface NV, you can see a wide variety of materials that have non-unitary magnetic permeability that are detected. You have an iron oxide, you have a bismuth ferrite, you have a pyrolytic carbon over here. Even bismuth has a sufficient response that it might be detectable. And the line for a ferromagnet with a divergent permeability and a superconductor whose magnetic permeability is 0 is the same because the size of the image spin is going to be the same. All right, so what's the possible implications for this kind of sensing approach? Well, one idea would be to think what happens when you look at magnetic material where the top of that magnetic material has been deactivated, it's made inactive or dead, perhaps through oxidation or some other effect. This is a common event in magnetic materials. And so we imagine that you have a situation where you have a magnetically active material with the magnetically dead layer on top. And the question is, how thick is that magnetically dead layer? Ordinarily, you might have to do neutron scattering in order to, or X-ray scatter in order to figure this out. It should be quite intense. But here, it's possible to detect that because the response of the magnetically inactive material, the dead layer, is quite different. And so the accuracy in determining how far away you are from the magnetic layer is shown here in angstroms. And so if you are at 0.1 angstroms, that means that you should be able to tell which atomic layer is dead and which is not. If you then go over to see where the state of the art is, which is this green line of 0.1 kilohertz, you see you should be able to detect where that sits up to about 10 nanometers. So this is roughly the state of the art indicated here by the blue lines. All right, now let me move to another form of hybrid quantum sensing, which is related to the sensitivity to electric fields. So as shown in earlier work, the electric field is detectable through its shift in the precession frequencies, as shown here. And so we're going to see if there's another way that we can take advantage of this electric field sensitivity, in particular to detect single photons. So when we think about how we couple light to electronic properties, there are a variety of ways that one might approach getting single photon detection. So typically, one can imagine changing the discrete state occupation, as indicated here. One can change the discrete state energies by shifting them in response to some effect, or you can change collective state properties, such as you might have in a superconducting nanowire detector. Now, there's actually a connection between these first two, because an initial change in the discrete state occupation can produce a long-range effect through a field, say an electric field, magnetic field, whatever, which then modifies the discrete state energies of another entity. And that's in fact what we're going to look at. So we might speculate on what a coherent state single photon detector looks like and imagine that you have a dynamic charge polarization. It's the dipole that's induced in matter by the electromagnetic wave, indicated here, and that's going to modify the behavior of several two-level detectors that are around it. And that modification will depend on the electric field lines surrounding it. And as an example where we're looking at static rather than dynamic polarization, we can take this example from the literature where a photoresponsive molecule was used to change the gate bias on graphene transistor in response to light. So this is a photoresponsive molecule known as pyrene tethered disperse red 1, and it has a conformational change that causes a change in the electric dipole upon the absorption of light. That change in the dipole was used to change the charge density on a gate and thus turn on a graphene transistor. And there are some approaches where you could switch on or off quantum transport to get single photon detection, as described in this reference down below. Now, what we propose is something a little more, a little different, using the quantum spin sensor instead. So the NV is responsive to the local electric field. If you change the conformation of a molecule, as indicated here, here's the ground state configuration, here's the excited state configuration. So there's a ground state dipole and an excited state dipole. As a result, the electric field acting on the NV is going to change, and the energies of these three states of the spin 1 will also change. For more details, you can see our archive paper on this. Now, this is going to be then detected by changes in precession frequency, which means you require a certain amount of time. For general coherent detection, you have a system responding to a different set of energy levels, which is then processing. So it has to evolve for some time in order to have this effect detectable. And the minimum error that you have relates to the precession time versus the decoherence time. And so the challenge you have here is that the two outcome states aren't orthogonal. When does the photon arrive and how long is the spectrum changed? How do you distinguish in an optimal way two outcome states that are not orthogonal? And there's a quantum measurement formalism for this situation. It's using positive operator valued measurements. And so here measurements of non-orthogonal states are done so that false positives are suppressed as much as possible. They're placed in an error bin. And we use here quantum measurement theory to determine optimal distinguishability between the two outcomes. And the flowchart for how this is done is described here, where you calculate a time-dependent density matrix depending on what the electric field is going to be. You construct the relevant matrix here and find its eigenvalues, and then you calculate the optimum POVMs and get the minimum error probability. So here's a calculation of this minimum error probability as a function of time as the system is processing around. In fact, you find that in the POVM basis, the optimum error rate is better than it would be using a standard basis. So how would you use this in a kind of coherent detection protocol? Well, you're going to have a different outcome if you reset the spin and look at its precession, if the electric field is there versus if it is not. So you're going to imagine doing a continual reset followed by a measurement, which will take you a certain amount of time, indicated here is T-min. And then at some point, the photon will arrive, you'll get a switch, and you'll have a less optimally configured state of the spin center here, and it's unclear whether you will be able to determine that the photon is detected or not, but in the next cycle where the electric field is present the whole time, you definitely will. And so therefore your arrival time sensitivity is given by this minimum time as you do the continual reset and then detection. Now there's another wrinkle that we can explore here, which is using multiple spin centers, using multiple NVs positioned around. Each of those will process independently in the electric field produced by that dipole, and the error rate is suppressed dramatically as you increase the number of NVs for sensing. And that's indicated over here on the left as you see an exponential suppression of the error rate as you have more and more spin centers that are responding to that absorption. All right, so to summarize, we have here described some new directions in hybrid quantum sensing. There's magnetic back action on the sensing spin. It's sensitive to the magnetic response of the sample with minimal perturbation and can detect magnetic dead layers and buried magnetic regions. There's single photon detection, where you can convert from dynamic excitation to static perturbation using a photosensitive molecule. And here you detect with the coherent evolution of the altered spin structure and the perturbation. You can also distinguish between with and without using optimal state discrimination, which can be done within a POVM formalism. There's no impediment to adding multiple coherent sensors in the vicinity of the static perturbation. And you have frequent initialization and observation, so in principle this could allow all electrical devices. Now, looking forward, one can ask, is it possible to detect the dynamic excitation of the electromagnetic field? And here there may be prospects for coherently mixing the coherent spin center's electronic structure and the excitation frequency, but that's not something that we have described in this work here. So again, thank you for watching this video. Hope you enjoyed it, and I sincerely hope that we will be able to do this in person in 2021.